So here we're going to see how, what conclusions we can get from our experiments. So let's say again that you have, you're doing this, you have your best estimate, and you're comparing that to an accepted value. And this is going to, these numbers don't match, so there's a difference between them, and that difference we're going to call the discrepancy. So the goal of the experiment, or yes, we'll just say the goal of the experiment is going to be to, be as accurate as possible, or to make the best estimate as close as possible to the accepted value. And what that means is that ideally you want to make the discrepancy approach zero. It's never going to be zero, but you can try to make it as small as possible. I mean, there's nuclear physics experiments where they get the percent difference down to about 0.0000. I'm not even sure they can go to 9 places there. So it's not zero, but it's a very small value. So that's going to be the goal, to get the percent discrepancy as small as possible, even though it's never going to be zero. So how can we get a conclusion out of this? So let me show you here. Let's say again that you have I'm going to write my values along an axis. So this is your best estimate here. And this is going to be your accepted value here. So we're going to see a good experiment because we want the discrepancy, or the difference between them, to be small. So we're going to say that if this condition applies. So remember that the best estimate, it has an error. It has a range. So it's going to be best estimate plus some value, and then minus that same value again. And so here we're going to say that for a good experiment, this value here, we're going to take that to be 2 times the error. So we're going to compare the discrepancy to this thing here, 2 times the error. So we're going to say that if the discrepancy is less than 2 times the error, then this is going to represent, then that means that this value is small enough. And so this is going to correspond to a consistent experiment, or that your measured value and the accepted value, or your measured value is consistent with the accepted value. And if the discrepancy is greater than 2 times the error, then this is a really big number, so that means that they're too far apart, and so this means that your measured value is going to be inconsistent with the accepted value. And the other case, if the discrepancy is close to 2 times the error, then this is going to be inconclusive. Here we're going to learn about random errors, but before we do, we're going to learn about what are called systematic errors. So what is a systematic error? So let's say you have an example like this here. So let's say that you have a meter stick, and one person, let's see, they look head on onto the meter stick to get their readings, and somebody else constantly looks at the meter stick at an angle here. So they're going to get different readings. So the person here, let's say that they get a reading of 1.5, and a person off to the side here, they can get a reading of consistently 1.7. So their readings are always going to be consistently off by 0.2, or off by the same value. And another case similar to this is where you have a kind of a balance beam, and you want to measure the weights of 2 objects, but the balance beam throughout the whole experiment isn't calibrated, so it's off to the side, so it's not well calibrated. So you're always going to be off by the same value. So these kinds of errors are called systematic errors, where it's based on consistently the same error applied to every single experiment, or every single measurement. There are other kinds of errors that aren't systematic. For example, let's say that you have a table and you have a laser, and then you're using a laser to sight something onto a screen there. And so everything is well calibrated, but you're in a building and the building shakes or the building has vibration. So the table is going to vibrate up and down. So what that's going to do is that it's going to cause the laser light to actually vibrate around here. It's going to vibrate back and forth. So here, then this is going to be a random vibration here. And at random vibration, this is going to cause random errors. And this is going to be the next thing that we're going to be looking at. So just to clarify, systematic errors are the same for every measurement. They're off, so each measurement is going to be off by the same value. So these are actually easy to identify. But random errors, the errors are different for every value. So these are harder to identify. So we're going to have to apply statistical tools to take into account random errors. And the first tool is we're going to take our best, if there's random errors, we're going to take our best estimate to equal the average of your measurements. So in statistical terms, the average is written like this: F bar is equal to the summation of all your measurements divided by the number of measurements, or the mean. And we're going to say that your best estimate is going to equal the average. So this is for when you have to take into account random errors. And how do you get the error? So the way to get the error, it's a two-step process. So first thing you're going to do is to find the standard deviation, and that's defined by this formula. It's going to be the sum of your measured value minus the average squared, and divided by the number of measurements minus 1. For large measurements, n becomes really large. It can be as much as 1,000 or 1,000,000. So that means that the 1 here can be insignificant. But in general, it's going to be over n minus 1. But this is not the error. We're going to define our error to be this. We're going to call this the standard deviation of the mean. And a formula for this then, so the error is going to be given by this. It's going to be standard deviation of the mean, and it's going to be the standard deviation divided by the square root of the number of measurements. So this is going to be the error. This is going to define the error for when you take into account random fluctuations. So in this case here, then your measurement is going to be defined like this. Is going to be the average plus or minus the standard deviation of the mean. And you can also write this using fractional errors, but I think this is good enough for it now. And so in general, to be more accurate, your total error takes into account both systematic and random errors. So then we can say that the total error for x is going to equal the square root of the systematic errors, the things that are constantly off by the same value, plus the standard deviation of the mean squared.